All right, so we're going to do an application of a partial sum of an arithmetic sequence. In 1970, the median age of first marriages for U.S. men was 23.2. On average, this age has increased by approximately 12 hundredths per year. We want to write a formula for the nth term of the arithmetic sequence that describes the median age of first marriage for U.S. men n years after 1969. And then we want to figure out what the median age for first marriages will be for U.S. men in 2025. So we'll start by writing our formula. Remember that our generic formula for the nth term of an arithmetic sequence is a sub n equals a sub 1 plus d, which is our common difference, times n minus 1. So a sub 1, notice how it said that n is the number of years after 1969. So when they give us that amount, that age of 23.2 for 1970, they're giving us a sub 1 because that's 1 year after our 1969. So we'll have 23.2 plus our common difference. Well, our common difference is what it increases by every time, and it said it increases by 12 hundredths every year. And then we have our n minus 1, and that's it. In part B, we're going to use that equation to find the median age happening in 2025. So I guess we need to figure out our n. What's our n going to be? We're looking for the number of years after 1969.
Is it 55?
55. Well, okay, so wait a minute. Actually, we're going to be
Years are weird.
I know, right? I end up counting them on my finger all the time. So actually, because we're started after 1969, because you get that 55 if you do 2025 minus 1970, but we actually got to go back all the way to 1969.
Okay.
So our n
56.
is actually 56. I know, I do. With the years, I'm always counting on my fingers.
Yeah.
So a sub 56, that's going to be 23.2 plus 0.12 times 56 minus 1. If we pop that in our calculator, anybody get an answer? And let's just like, I don't know, round to the nearest tenth.
I got 29.8.
All right, sounds good to me. Questions, anybody? All right, so that's an arithmetic sequence. Those are sequences that we are repeatedly adding or subtracting a particular number. Now we're going to move on to geometric sequences in series. A geometric sequence is a sequence in which each term after the first is obtained by multiplying the preceding term by a fixed non-zero constant. So instead of adding over and over again, we're multiplying over and over again. The amount by which we multiply each time is called the common ratio of the sequence. To find the common ratio, because sometimes it's a little tricky to see, the common ratio R is found by dividing any term after the first term by the term that directly precedes it. And that's similar to what they told us to do to find the common difference. They said take any term and then subtract the one before it, but usually we could just look with our eyes and tell. But here you may want to actually do the division. A geometric sequence with a positive common ratio other than 1 is an exponential function whose domain is a set of all positive integers. So let's write the first 5 terms of the sequence where a sub 1 is equal to 4 and r is equal to 3. So how do you know, right? Because on my math lab, it might just say write the first 5 terms of a sequence, and how you know that it's geometric versus arithmetic. Geometric is going to say r equals, whereas an arithmetic is going to say d equals some kind of number. So just heads up on that. So let's write out our first 5 terms. They give us the first one, and then we're just going to multiply by our common ratio r equal to 3 over and over again. So a sub 2 is going to be 3 times 4, which is 12, and then a sub 3, it's going to be 3 times 12 again, 36, a sub 4, 108, and a sub 5, 324. So here are the first 5 terms of our arithmetic sequence. Questions, anybody? All right, in our next example, our formula has been written as a recursion formula. Remember, when we recognize that it's a recursion formula, when we have this kind of n-1 subscript, that this a sub n-1 tells us to be working off the previous term. So what we're going to be doing here, we're starting with a sub 1 equal to -2. And then our recursion formula tells us to multiply the previous term, a sub n-1, by -6. So -6 is our common ratio, and we'll just start multiplying. So a sub 2 is going to be 12. A sub 3, -72. A sub 4, 432, and lastly a sub 5, -2,592. Questions at all? Like our arithmetic sequences, we have a formula for the general or nth term of a geometric sequence. The nth term of a geometric sequence, with the first term being a sub 1 and a common ratio of r, is defined to be a sub n equals a sub 1 times r to the n-1 power. So I feel like this is really similar to the arithmetic one, which was a sub n equals a sub 1 plus d times n-1. So we're starting with each of these with our a sub 1. With the geometric, you're multiplying by something over and over again. And with the arithmetic, we're adding by something over and over again. And shorthand for repeated multiplication involves exponential notation, whereas shorthand for repeated addition is multiplication. So we have this, whatever our common ratio or common difference is, and then the n-1. So I see these as very similar equations. It's just one's multiplication and one's repeated addition. So let's find a sub 5 when a sub 1 equals 5 and our common ratio is equal to 3. plugging in our formula, we're going to have 5 times 3 to the n minus 1, so 5 minus 1 power. And like, I don't have a cool story about a mathematician like I did for Gauss with the nth term of an arithmetic sequence, but I kind of feel like it makes the same kind of sense, that we're doing the n minus 1 because we're doing, if we're starting with a sub 1 and we don't want to multiply it by anything, we need to have an exponent of 0 on that common ratio. So n minus 1 is what's going to give us that 0. All right. Anyways, let's pop this in our calculator. I get 405. All right, why don't you guys try the next one? The answer is horrible. I'll just warn you ahead of time. So if you put it in your calculator, you're going to get an awful decimal. It'd be great if you got a fraction, but that's going to be awful too. Here, I'll even put you guys in groups so you can commiserate with it. All right, so finding the sum of the first n terms of a geometric sequence, our partial sum S sub n is given by a sub 1 times 1 minus r to the n power, all divided by 1 minus r. This is where a sub 1 is our initial term and r is our common ratio. So we need 3 different things to find the partial sum of a geometric sequence. We need to know the first term. We need to know our r value. And we need to know the number of terms. So let's find the sum of the first 12 terms of the sequence 3, 6, 12, 24, and so on. So we need to get our 3 things. A sub 1, our first term, well, that's 3. Next, we need to know our R value, our common ratio. What's that going to be?
2.
It's going to be 2. And then our N, well, that's going to be 12, and we plug it into our equation. So S sub 12 is going to be 3 times, I'm sorry, hold on one second. I love that my kids always have to have a 10 o'clock video chat right in the middle of all my classes. And 3 of us have a video chat at 1 o'clock today at the same time. So that's going to be fun. All right, so 3 times 1 minus 2 to the 12th over 1 minus 2. So this becomes 3 times 1 minus 4,096 over negative 1, for a partial sum of 12,285. And I know that number seems like crazy huge since our sequence was these relatively small numbers. However, this is a geometric function here, right? These sequences are represented then by exponential functions, a geometric sequence exponential function, and we know that exponential functions grow really, really fast. So we should not be surprised that we got this large partial sum for only 12 terms. Questions at all? All right, so our next two, we're finding a partial sum, but this time we're in summation notation, and then the next one is an application. I'm gonna put you guys in groups, give you like 5 minutes to try these two.
So we can use,
Oh,
we can-
sorry. Dang it. I'm just talking and talking with my mic muted. Sorry. Go ahead, Anna. What's your question?
yeah, I didn't know you were talking.
No, that's my bad again.
So the sum notation, we can use both notations like S sub and that sigma, but that means the same sum.
Mm-hmm.
Oh, okay.
Yep.
Thanks.
All right, so I'll re-say everything I just said. So to get our a sub 1, all we're doing is plugging 1 into our formula here for I, and we get negative 12. The R value, that's whatever is being raised to the variable power. It's the base of our the exponential portion of our function. And our n values up top. So then we plug it into our formula. Anybody have any issue getting a partial sum of negative 6,564? All right, so then we had the application problem. A sub 1 was given to us. The tricky part was definitely identifying the R value. You know, it's tempting to make our R value just 0.05, but that's the raise amount, and we're trying to add up salaries. So to get your salary, you have to take your salary plus the raise. So the 1 is whatever your salary was, and then that 0.05 is the raise to it. So we have an R value of 1.05. So starting at $24,000 with a period of, I'm sorry, over a period of 20 years, getting a 5% raise every year, which is a huge raise, by the way. Okay, people don't usually get 5% raises. You're still only going to make in your 20 years $793,582.89. Questions at all on finding a partial sum of a geometric sequence? All right. So a geometric series, we know series just means add up the sequence. So an infinite sum of this form, which is, you know, just our crazy form of what all those terms added together would look like. The first term, a sub 1, and our common ratio R, this is called an infinite geometric sequence. So this is about to be one of those topics where I feel like it is just mind-blowing in math. I have this great appreciation for math, but sometimes like I'm like, oh yeah, that makes sense, and sometimes I feel like my mind gets blown. Well, this is one of these times where I feel like my mind gets blown. To determine, okay, so basically we're going to take an infinite sequence, an infinite number of numbers, and add it up and get an answer. I mean, that's just, even saying it out loud seems crazy. To determine whether an infinite geometric series has a sum or not, we have to look at what happens to R to the n as n gets large. So not every one of these infinite series actually has a sum. So if our R value is any number between -1 and +1, then the term R to the n approaches 0 as n gets large. See, so when it says in between -1 and 1, that means that it's let's get rid of the negative, a number less than 1. And when you multiply a number less by a number less than 1, it gets smaller. Sorry, I'm fumbling over my words here. So if I take a number and I multiply it by 1, it stays the same. If I take a number and I multiply it by something greater than 1, it gets bigger. But if I take that number and multiply it by something smaller than 1, it gets smaller. So the only time an infinite geometric series actually has a sum is if that common ratio is something smaller than 1. It could be positive, it could be negative, so that every time we multiply by that common ratio, our number is getting smaller and smaller and smaller. if our number just kept getting bigger, well, then we wouldn't be able to get a definite sum because, well, it's just going to add up to infinity because I'm adding larger and larger and larger numbers together. Does that kind of make sense? All right, well, if our term r to the n approaches 0, when r is in between -1 and 1, we can simplify this formula. So if this becomes 0 here, and we clean that up, then we end up with s being equal to a sub 1 divided by 1 minus r. And you'll notice the difference in the notation. It no longer says s sub n, it just says s, which means it's the sum of all the numbers. Whereas that notation s sub n means, well, it's the sum of the first, 17 numbers or whatever. So when you don't see that n there, that means that it is an infinite series. And if your R value ends up being something greater than 1, then this series does not have a sum because it's going to add to infinity. It's kind of like with the horizontal asymptotes with a rational function. When the degree of the numerator is larger, there is no horizontal asymptote because you're not dividing by something that cuts the number down. It just grows and grows without bound. But when the degree of the denominator is larger, then it tends towards 0 because we're dividing and our number is getting smaller and smaller. I always link it to that. That makes sense in my brain. All right, so let's find the sum of each infinite geometric series if it exists. So the first thing you want to do is find your R value because that's going to tell us whether this infinite sum even exists or not. All right, so a sub 1 is going to be 1, but we definitely need our R value. And to get our R value, you take your second term and you divide it by your first term. And we're good to go because we ended up with something less than 1. Again, it could be positive, it could be negative. So now we can take our a sub 1 and our R and plug it into our formula, our infinite series. We're going to get 1 over 1 minus 1/4. So we get s to be equal to 4/3. So if you take these numbers, right, 1 plus 1/4 plus 1/6 plus 1 over 64 plus, what's the next one going to be? 1 over 243. That's not right. 256, 1 over 256. And if you just keep adding up those numbers to infinity, it becomes exactly 4/3. That's like crazy to me. All right, let's try the next one. A sub 1 is 5, so let's check out what our R value is. We take our second term and divide it by our first term. We're getting 1/6. So that means that our sum is going to exist because we have a number less than 1. Our infinite sum is going to be 5 divided by 1 minus 1/6. So that's 5 divided by 5/6. We get an infinite sum of exactly 6. Questions, anybody? All right, I'm going to put you guys into groups and let you do the next two. All right, so first one did not exist because we had an R value greater than 1. Our second one, we had an R value of negative 0.7, so our infinite sum did exist. We get 120 over 17. Questions at all on geometric sequences? All right. Well, the next thing we're going to learn is mathematical induction, which is a proof writing technique. Honestly, I don't ever remember doing this in calculus. I don't ever remember doing proof by induction until real analysis, which are the classes that are like past calculus, the calculus sequence where it explains why everything in calculus works, like the math behind the calculus in real analysis. So I don't know, this is not the most important thing in the course. However, learning to write proofs is important. I mean, you're going to write proofs in calculus. For those of you who have to take discrete, that's an entire proof writing course. So I don't know, maybe induction will pop up in discrete as well. I feel like the first time I do this, you're going to be like, this is crazy. But then after that, you're going to see it's the same pattern over and over and over again. You just got to get comfortable with the pattern and kind of remember the steps. So the principle for mathematical induction says that if we let S sub n be a statement involving the positive integer n, and S sub n, it still means partial sum. That's still true. If S sub 1 is true and the truth of the statement S sub k implies the truth of the statement S sub k plus 1 for every positive integer k, then the statement S sub n is true for all positive integers n. Okay, so we know that sometimes we get lucky in math, like sometimes a trick will work once, but it doesn't always work. So that's what's happening here with this mathematical induction technique. They're saying, well, the first thing you got to do is make sure that it's true for the first one. We got to prove it works for something. Then what we're going to do is that we're going to assume that it works for S sub k. And S sub k, k is just, you know, a generic term, the kth term. It's not the nth term. It's in between the first term and the nth term in the list, but it's just like some random k, some random term in the list. If we assume that our formula works for the partial sum for the first k terms, if we can then mathematically prove that it works for the next term, the k plus 1 term, then it's not, ooh, we got lucky. It's saying, yeah, it really is following this pattern, even when we're being generic. Therefore, it's going to work for all n. So that's kind of how induction goes. So these are our steps in our proof by mathematical induction. So again, we're going to be given some partial sum statement, S sub n be a statement involving the positive integer n. To prove that S sub n is true for all positive integers, the first thing we're going to do is show that S sub 1 is true. So we're literally going to plug 1 in the formula and see if we get the first number in the sequence. Then we're going to assume S sub k is true and prove that S sub k plus 1 is true. I actually don't even really like, even when we're in class, I don't love to do this on the tablet because I like us to be able to see the whole thing at once. So I'm probably going to do some scrolling back and forth. At least you'll get to see it all at once on your paper. So like I said, the first one's probably going to seem crazy, but it follows this pattern. So just relax the first time through. Every time you do one, it's going to make more sense. And I like to do a lot of show lines because it's easy to get lost in our own work. So here it goes. And I usually just start off a proof with PF just because sometimes I do side work ahead of time and I just want to announce that, hey, I'm actually starting my proof. All right, the first thing that we're supposed to do is show that S sub 1 is true. See, because what's happening here, I guess I should start with that, with what we're even trying to prove. We're trying to prove this statement by mathematical induction. Now, we got a formula for the partial sum for an arithmetic sequence and a geometric sequence. So what's happening here is they're just saying that if our series follows this pattern 3, 4, 5, 6, and so on up to n plus 2, to find the partial sum, we can plug it into this formula over here. So it's just proving additional formulas is what we're doing here, which is why it falls in with this sequences and series. All right, so we're showing that S sub 1 is true. So all I'm going to do is plug 1 into this formula here and then make sure that I get 3. And I do. Great. Next, we're going to assume S sub k is true. Well, what does that even mean, right? So then I like to do a next line where I'm kind of explaining what that means so I know what I have to use. So if we're assuming that S sub k is true, oh man, guys, I didn't realize I was so far over class. All right, you guys want me to just stop? I didn't realize it was 10:40. This is going to take me 10 minutes to do.
Oh.
I don't mind if we keep going, but I know other people might have things that they need to do.
Yeah, sorry, I didn't notice the clock. So yeah, let me ask everybody. You want me to keep going? It's going to take me 10 minutes.
I'm fine with it.
Do it.
All right.
Yeah, why not?
Well, I just always like to try to be respectful of your time. In class, I got you locked in, but you know. All right. So what does it mean for S sub k to be true? That means that, remember, S sub k is the partial sum of the first k terms. So that means that 3 plus 4 plus 5 plus all the way up to not n plus 2, because the n term is past the kth term. It means that up to the k plus 2 term is going to be equal to k times k plus 5 all over 2. So basically all I did was take my original, what I was given, and I put a k in where the n's are. So it's saying that if we get up to the kth term, then we just plug k into the formula, which makes sense because to find S sub 1, that's what we did, right? We just took 1 and we plugged it into the formula for n. So S sub k would simply be, hey, take k and shove it into the formula for n. I might even want to write S sub k equals that. All right, so that's what we're assuming. Now, we want to show that just because it worked for one, it doesn't mean it's going to work for all. So now we need to show that it works for the next one. So we want to show that S sub k plus 1 is true. Well, again, what exactly does that mean? So I like to do a second show line kind of explaining what that means. I'm saying then that S sub k plus 1 is going to be equal to 3 plus 4 plus 5 plus. Now, the kth plus 1 term is just one term after the kth term. So if this right here is S sub k, then S sub k plus 1, the next term is going to be k plus 1 plus 2. We're trying to show that that's going to be equal to, and now we're plugging k plus 1 in for n. All right, so again, basically, I just went back to my original that I have highlighted there in yellow, and I basically just put k plus 1 in for k. The only difference is I have this like extra term right here to show that this is the kth term. And then this right here is the k plus 1 term. All right, and then I think I'm going to clean this up a little bit right here. K plus 1 times k plus 6 all over 2. All right, so we want to show that s sub k plus 1 equals k plus 1 times k plus 6 all divided by 2. So now let's try to do that. So I'm starting with s sub k plus 1. And I'm basically kind of just rewriting this portion of what I have. All right, so s sub k plus 1 we know is equal to this. And that k plus 1 term, I'm just going to write that k plus 3 to clean it up. Well, this first part right here is s sub k. Right? If we take a look up here, we assume that, that's s sub k, and we're assuming that that's equal to k times k plus 5 all divided by 2. So what we're going to do is we're going to substitute that beginning part with k times k plus 5 all over 2. Because that's equal to s sub k, and we set up here that that's what s sub k was, so we're just going to put it there instead of that list of numbers. But we still have this plus k plus 3 on the end, so we still have to keep that. And we're going to do the same substitution every single time. We're going to do it the same way, and then we're going to substitute everything except the last term for whatever we assume s sub k to be. And now we need to add up what's left. So I'll have to get a common denominator. I'm definitely going to run out of room here. So multiplying top and bottom by 2. It's going to be 2k plus 6 all over 2. Guess I should have distributed there. I'm going to distribute and put them all together in one fraction since we have a common denominator. So this is going to be k squared plus 5k plus 2k plus 6 all over 2. Which is k squared plus 7k plus 6 all over 2. And every time, that's what you're going to do. You're going to add together whatever you have left. Well, what are we trying to do? We're trying to show that s sub k plus 1 equals this over here. So now we basically just want to turn in what we have left into this. And it'll do that as long as we factor it. S sub k plus 1 equals, this is k plus 1 times k plus 6 all over 2, which again is what we were looking to show. That's what we were trying to get to. We've done that. Now we're just ready for our wrap-up statement. Therefore, by mathematical induction, S sub n is equal to n times n plus 5 all over 2 for all integers n. Questions? After you do like 5 more, it'll be better.
Well, real quick,
Yeah.
for like back with the k times k plus 5, where was the k plus 5 then? Is it because of the like kind of like series or whatever?
Well, that's what, so we got this k times k plus 5 up here because that's what we get when we plug k into the original.
Oh, okay. I got it.
Anybody else? All right, guys, it's crazy to me to think that this is our last week and then the final. So I'm going to get done what I can get done. I think I'm going to actually jump and do partial fraction decomposition first, so I make sure I get that done, and then jump back and finish as many of these mathematical inductions as I can on Wednesday, and then I'll try to have just a review day for you guys to just ask questions on Friday. Remember, I
It's
have office
crazy how
hours.
fast this went by. It's wild.
I know it is. Well, I mean, we always know it goes so fast, but I think we thought we were going to be in remote instruction forever. Yeah, it went fast. But you guys are all doing great. I mean, I feel like I've never had a class that's collectively done as well as you guys are doing. So that's super exciting for me. And the fact that I've had so many of you for so many semesters, it's just, you know, I'm so proud of you guys. You're doing so great. So anyways, I got office hours tonight. So if you have questions, pop in. I don't think I have a quiz, right? I don't think there's another quiz. By the end of the
Wait.
semester, I'm tired of grading quizzes.
Really?
My math
Don't-
lab.
Oh, is there one more? Oh god. Now I'm gonna have to look.
And there is one, the quiz.
I mean, you can take it out if you want.
Oh no, man, I
Yeah.
do have quizzes for 11 and 7.3. Damn. Everybody gets an A.
Let's go.
Yeah, anyways, if you guys have questions, see me tonight. Jordan, go back and watch the summation notation video so that any of this makes sense to you. And
Do that.
I'm gonna work hard to slap together some half-assed review packet for you guys today.
Woo!
Yay!
What time
Right?
do your office hours tonight start then?
7 o'clock for you guys.
Okay.
All right. If you want to text me or email me earlier to see, because I actually jump on at 6. I'm supposed to have a trig at 6, 103 at 6:30, and then you guys at 7. But I get more of you guys than anything else on my evening one. So if you want, you can just pop in early. I guess you don't even have to email me. You can just pop in early, and if I'm free, wonderful, and if I'm not, then I'll tell you to come back.
Awesome.
Okay. All right. Everyone have a wonderful day.
Take
Thanks.
care.
right.
Bye.
Bye.